If you've been following along with this series, you're probably feeling pretty good right now. We've managed to open up a window, draw a triangle, and all of that using the modern pipeline. It feels like we're building the foundations of a rendering engine. So, you search the internet and find shaders. Given the name, you think it's quite obvious what they're for. They're the scripts that calculate lighting and shading, right? That's only half the picture. Stay with me till the end of this video and I will show you the full picture. Welcome to the 6th episode of my OpenGL series. Today we'll learn all about shaders. Rendering graphics requires a huge number of mathematical calculations. Say we're rendering a triangle on a 1080p display. Depending on the size, there could be hundreds of thousands of pixels to be drawn for that triangle. Drawing these pixels on the CPU would take ages, and so we draw on the GPU. We sent the vertex data to the GPU in the last video. Now we need to tell the GPU what to do with that data. This is where shaders and the whole graphics pipeline comes into play. Shaders are simply programs that run on the GPU, in much the same way that programs run on the CPU. However, with one very important advantage: parallelism. In the last video, a triangle may have appeared for some of you but not for others. That is because we didn't write a shader for it. Depending on your drivers and GPU manufacturer, a default white shader may be provided to the program in case it is missing one. It doesn't need to be provided as it isn't in the OpenGL specification. There are lots of shaders: Vertex Shader, Fragment Shader, Geometry Shader, Compute Shader, Tessellation Shader, etc. For most of the series, we're going to focus on Vertex and Fragment shaders. The simplified graphics pipeline looks like this. The Vertex shader runs once per vertex. The primary purpose of a vertex shader is to tell OpenGL where you want that vertex to be in the clip space. For those of you who are paying close attention, this might seem trivial. I mean, we're already specifying the vertex positions in our buffer. So why do we even need a vertex shader, right? Suppose we have a camera in a 3D world and it has some position and rotation. The vertices that we have specified in the buffer aren't going to translate directly to the screen now. So vertex shaders handle these transformations. It also makes more sense to do those calculations in parallel on the GPU than on the CPU. The fragment shader, also known as the pixel shader, runs once for every fragment that needs to be rasterized. Fragments are different from pixels, but for now you can think of fragments as pixels. The primary purpose of a fragment shader is to determine the color the pixel is supposed to be. While rendering a simple triangle, a vertex shader is called 3 times, while a fragment shader is called hundreds of thousands of times. So we need to be very careful about where we do our calculations. Otherwise, we might end up repeating the same task unnecessarily, slowing down performance. Okay, now let's look at the code. Let's go to the bin folder, which is the output folder. Create a folder called shaders and create 2 files: triangle underscore vs.glsl and triangle underscore fs.glsl. GLSL stands for OpenGL Shading Language. Don't worry, it is very similar to C++. In the Vertex Shader, we first need to specify the OpenGL version. I'm going to use the latest OpenGL version supported on my GPU as of recording this video, which is 4.6. It is written as 460. Similarly, if you're using 3.3, then write 330. We're also using the core profile since we're using modern OpenGL. Next, we need to declare the shader input parameter position. We need to specify the layout location, which is the attribute index. Here, 0 means that this data is the first to appear in the vertex. You'll notice that the vertex data that we're passing is 2D, but the data that the vertex shader receives is 4D. We're doing this because we'll eventually need 4D data to perform transformations and all. OpenGL will convert this data for us. The missing Z component will be set to 0 and the missing W component will be set to 1 since it is a position. We'll talk about homogeneous coordinates in a later video. In the main function, we'll set gl_position to position. It is important to note that gl_position is a vec4. That's all for a basic vertex shader. In the fragment shader, again, we'll specify the OpenGL version. We'll declare the output color. In the main function, we'll set this color to any RGB value that you like. Note that alpha won't actually make a visual difference here. The alpha component is written to the frame buffer, but transparency won't appear until we enable blending and set a blend function. Let's keep things simple here. We'll do that in a later video. We're done with writing the shaders. In the project properties, go to debugging and make sure that the working directory is set to out there. This way, we won't have to keep a copy of our shaders in the project directory. We can just ship the program with the shaders and resources directly. I like to put the code for managing shaders in a class. There are many ways to abstract this. Here's the approach that I prefer. Let's create the shader class. We'll add a private variable m_shader ID. This is the ID of the shader program that will contain both the vertex and fragment shaders. We only temporarily need their individual IDs. We'll add a public constructor. In it, we'll take the name of the shader and we'll also add a destructor. Let's create two private functions, read shader file and compile shader. In the constructor, we'll read the sources of both the vertex and fragment shaders. Then we'll create a shader program and compile both shaders. Next, we'll attach both shaders to the shader program, link the program, and validate it. GL validate program checks things like whether the required text units and the required buffers are bound. It is optional, and note that it is not intended to be called during production use. Since OpenGL has already passed the shaders onto the GPU VRAM, we can clear the resources from the CPU RAM by calling gldelete shader. This function only marks the shaders for deletion. The actual cleanup happens after they're detached. Finally, we assign the program variable to m_shader ID. In the destructor, we simply call gldelete program with the shader ID. In read shader file, we'll create an input file stream. If the file is open, we use a string stream buffer, and finally we return the buffer string. In compile shader, we'll first create a shader and get its ID. Let's store the address of the raw string data of the source in a variable. We'll then call GLShaderSource to assign source code to the shader. The first parameter is the ID. The second parameter is count, which is the number of strings that make up the shader source. Now, OpenGL allows you to split the source into multiple strings, which will then be concatenated in order. We don't have multiple strings, so it will be one for us. The next parameter is called string. This is the array of strings that make up the shader source. will pass the address of src. The last parameter is the array of the lengths of strings. We don't want to deal with the lengths of strings, so we'll pass a null pointer, in which case it considers these strings as null terminated. Our strings are already null terminated, so we're good. Then we'll compile the shader. Next, we'll create a glint result. We'll call glGetShaderIV to get the compilation result. If the result is GL false, that is, the shader encountered a compilation error, we'll get the info log length then get the info log, print it to the console, flag the shader for deletion, and return 0. The info log contains line numbers and detailed error messages, which are invaluable for debugging. GLDeleteShader only flags the shaders for deletion. The shader is actually deleted when it's no longer attached to any program. If the shader was successfully compiled, we return the ID. While we're at it, let's add 3 public functions: ID, bind, and validate. In ID, we'll simply return the shader program ID. In bind, we'll call GLUseProgram with the ID. The purpose is to select this shader for use by OpenGL. In the validate function, we'll call GLValidateProgram. Next, we'll get the program status. If it is GL false, then we print the info log. In a later video, we'll also add support for uniforms, the way we pass data from the CPU to the shader. Since we've already done most of the heavy lifting, to use a shader, we'll create a shader object in the main function and call its bind function. Before calling GLDrawArrays, we'll call the shader's validate function. Run the code and you'll see a colored triangle. So the full picture is, shaders aren't just for lighting. They're the programs that define every stage of how your geometry becomes pixels on screen. In the next video, we'll work on abstracting the vertex buffer object and clean up the code. If you found this video helpful, please like, share and subscribe. I'll see you in the next one.